Okay, so in this example, what we're going to do is, given a graph, we're going to look at how to construct the minimal spanning tree of that graph. Okay, let me see. Okay, um, so the first step is, of course, you're going to use Kruskal's algorithm here. So the first step in Kruskal's algorithm is to sort the edge weights. So given a graph like this, we need to be able to sort the edge weights and consider the edges in the increasing order of edge weights. Now, in Kruskal's algorithm, also each vertex is initially said to be in its own component. So S is in its own component S, identified with S as the label of that component. Um, W is in its own component as W, X is in own component as X, and so on. So each vertex is in its own component. So in each iteration, we want to merge two components and make them as one component, and relabel the components a with a component ID that is essentially the smaller of the two component IDs. Okay. All right. So the smallest weightage is 1, and there's a tie. You can choose either this one or this one. So let's say I pick this edge of weight 1. So check its end vertices. So the way the convention I'm following here is the label outside the circle indicate actually the vertex ID, and the label inside the circle indicate the component ID. So initially both the vertex ID and the component ID are the same, each vertex in its own component. So now when we pick this edge WV, we want to check whether the two end vertices are in two different components, and they are. W is in component W, V is in component V, so we can merge the two components using that edge. So when we merge the two components, we have now both vertices in one component, so we need to relabel the component ID. So basically we pick the minimum of the two component IDs. So the W's component ID is W, V's component ID is V. So alphabetically or lexicographically, the W and V occurs before W, right? U, V, W. So we label them, the component vertices, as V. So now we repeat this process. There's another one here. So this is an edge connecting X and Y, and X is in component X, Y is in component Y. They're two different components, so you can combine. So that's the criteria. We have to have the two end vertices in two different components. So now we can combine the two components, and so the smaller of the two component IDs is going to be X. So we label the two vertices as being in component X. The next smallest edge weight is 2, and that's connecting U and V. U is in component U, V is in component V, so you can combine them, and that's this edge weight 2. And now you see here, this is in one component, right? U is in component U, V is in component V. So we need to when we combine them, they become part of one component. So we have to pick the minimum of the two component IDs. U is in component U, V is in component V. So the minimum of, or the lowest of U and V is U. So we even change these. So all these three vertices are in now one component. The next smallest edge weight is 3, and we say pick this 3, and which means connecting W and Y. W is in component U, Y is in component X. Still they are in two different components, so we can connect these two components basically using this edge. So when we combine them, we have to pick the minimum of U and X for the component ID, and it happens to be U. So we can again relabel the component ID of X to be U and the component ID of Y to be also U. So now you have the next smallest weight edge is 3, but if you choose say this 3 that connects basically V and Y, V is in component U, Y is also in component U. So if I add this edge 3 here, basically the two end vertices are in the same component, it's going to create a cycle. Okay, so we don't want a cycle, we want a tree. So remember that in each component we have a tree, we don't have any cycle in each component. So this is a component, no cycle, this is a tree, this is another component, no cycle, tree, this is another component connecting these three vertices, it's a tree, this is also a tree. So we don't want to create a cycle. So we discard or don't consider that edge from V to Y of weight 3, and let's pick up this edge from S to W of weight 3. S is in component S, W is in component U. There are two different components, so we can connect them. So which means between S and U, the lower component ID is S. So everything is now in component S. So if you add up the edges, these edges are the minimum spanning tree edges, and if you add up the edge weights, you will get the weight of the minimum spanning tree. In this case, it happens to be 10. So what it means is we cannot connect these vertices through edges such that the sum of edge weights is less than 10. 10 is the best or the minimum possible total weight of the edges. We cannot do better than that. Now, this is the same graph we used earlier for the Dijkstra's algorithm, and if we run the Dijkstra's algorithm, we get the shortest path tree, and if you, starting from a particular source, of course, which is S, so if you sum up all the edge weights of the shortest path tree starting from the source, it happens to be 12. So this is an example that we can use to say that the shortest path tree that is rooted at a particular source need not be a minimum spanning tree. Okay. Likewise, a minimum spanning tree is not specific for a particular source. It's for the whole overall graph. So there is no minimum spanning tree rooted at a particular source. It is for the overall graph spanning all the vertices and connecting them through edges such that the sum of all the edge weights is the minimum. Which means if I want to say this is our minimum spanning tree, go from the S to U, we know the Dijkstra's shortest path tree directly connects S and U. If you go back and look at it, the Dijkstra's shortest path tree directly connects S and U, but because that's the shortest path weight of weight 4, right? This is the best we can do, to go from S to U. The shortest path weight is 4. But if you look at the minimum spanning tree that we just found for Kruskal's algorithm, if you want to go from S to U on the minimum spanning tree, you have to go like this: S to W, weight 3, W to V, weight 1, V to U, weight 2. So the sum of the edge weights on the path is 6. So if you want to send information on the shortest path, you have to find the shortest path tree. Don't use a minimum spanning tree. A minimum spanning tree is typically used when you want to, say, broadcast information, okay, from one vertex to every other vertex, such that the total distance traveled across all the edges is the minimum. So even though individually it may take a little while, across all the edges it takes the total sum of the edge weights is the minimum. Okay, so that's the use of minimum spanning tree. Okay, let's take up another example. So given this graph, initially each vertex is in its own component, and so we start with the smallest edge weight, which is 5. So let's take up this edge. So A is in component A, D is in component D, so we can combine them. They are two different components and make them to belong to one component, and pick the smallest of the two component IDs, which is A. So we have them like this. The next smallest edge weight is this 5, and it connects C and E. C is in component C, E is in component E, so we can connect them, and that's also edge weight 5. The next smallest edge weight is 6, and 6 is connecting D and F. D is in component A, F is in component F. There are two different components still, so you can connect them. The next smallest edge weight is, say, 7. Let's say I pick up this 7, which is from A to B. So as you see here, of late A is in component A, B is in component B, still two different components, so you can connect them. Let's pick up this 7. B is in component B and E is in component C, still two different components, so we can connect them. And so we are right now like this. So you need to basically look for connecting G. So which means look at G. If you want to connect G to the rest of the component, this is the whole other component, we pick the smallest edge weight essentially. So instead of between 9 and 11, you will pick 9 that connects, and that's actually connecting E and G. E is in component A, G is in component G. So the two different components, so you can as well connect them. And now between A and G, it's the lowest of the two component IDs is A. So make sure you change the component IDs correspondingly as you merge the components. So in this case, this is component A, this is component G. So the smallest of the two component IDs is A. So we have to change this to A. On the other hand, when we merge, say, this component with this, the smallest of the two component IDs between A and C is A. So when you merge the two components, you have to make sure to change this component IDs of these vertices to A. Okay, so that's Kruskal's algorithm. We'll stop here.